All right, good morning. Welcome to Elements of Calc 2. So we're going to have a little review of integration here just to get us started. Okay, so when we are trying to do integration, we are undoing derivatives. Okay, so integration really means anti-differentiation. And pretty much we're just going to reverse the power rule for derivatives, right? If you remember, if I have to take the derivative, like say x cubed, the rule for derivatives for this, okay, d by dx here, taking the derivative. This 3 comes down in front, right? So we have, this is going to be 3 times x, and then what happens is we have 3 minus 1, and that's what's going to go on here. So we have the 3x squared. In order to do an integral, we just pretty much, we just reverse this operation. So if I'm going to go ahead, take, say, the integral of 3x squared dx. Now this integral sign and this dx, they work as a pair. Okay, what's really going on is we're summing up a whole bunch of tiny little areas, and what we're going to have here is that's the sum. That means we're never going to use this. Okay, so we're just going to start adding up, right? Alpha of xi's times tiny little delta xi's. Okay, and I guess infinity. Okay. Okay, so what's happening here is we're getting a whole bunch of these tiny little rectangles. These are these delta x's right here. Okay, adding up all of these little rectangles, these delta x's, that's the dx. So this works in tandem with the little delta x's have to work with sum because we're adding up tiny little rectangles. So that's why this dx has to be there. They have to work together. Back to just trying to take this integral and undoing the power rule. So what we're going to do is instead of subtracting 1 from the exponent, we're going to add 1. So we're going to say we're going to have 3x to the 2, okay, plus 1. But instead of multiplying, we're going to go ahead and divide by what we have left here. So whatever we have in the exponent, we're going to put on the bottom and say 2 plus 1. So we end up with 3x to the 3 divided by 3. These 3's cancel, and we end up with an x cubed. So we take the derivative of x cubed, we end up with 3x squared. Go ahead and take the integral of 3x squared, we're going to end up with x cubed. But let me ask you this. So if I wanted to take the integral of, say, 3x squared, and I wanted to, say, add 1 to this, okay, so let me go backwards and set to it that way. If I wanted to take the derivative of x cubed plus 1, so I want to take the derivative x cubed plus 1, we'd still end up with a 3x squared. The derivative of 1 is going to be 0. So that's, if I want to go ahead and undo this 3x squared, not going to necessarily get back my x cubed plus 1. Just going to get back 3. I'm going to get back an x cubed. But how do I know? How do I know which function I'm getting back? And do I know which one is it? The derivatives of both of these are 3x squared. So if I try to integrate either of these, I should get back something that looks like x cubed. But problem is that we don't know if it's 1 or 2 or like a square root of 5. We don't know. So when we go ahead and integrate this, we're going to get an x cubed plus a constant of integration. Okay, so this is just a constant that comes out. So under the derivative, if we go ahead and go back and take the derivative here, right, we're going to end up with a 3x squared, and the constant derivative of the constant is going to be plus 0. You don't have to add in 0 like this. It's not there. We just leave off as zeros. We don't worry about it. But when we undo this derivative, what we're going to have to deal with is there's a plus c at the end of this thing. Okay, that's your constant integration. Now, when you first learn definite integral, you might think, it's plus c, who cares? It matters, especially when we start getting the application problems a little bit. C's become really important. So you have to add in your plus c. You don't do that, that's like an automatic 2-point deduction problems. So don't forget your plus c's. It'll very easily turn like an A paper into a C paper, E paper. So you always want to remember your plus c for your indefinite integrals. Indefinite integrals, we don't have limits of integration. We don't have an A and a B sitting here. So right now, we're only going to be working about indefinite integrals. You don't have to worry about the A and the B. It's going to have a C. Okay. So that's the little first start here. The next thing that we're going to deal with is we're going to deal with a little example here. So if I have the integral of the square root of x dx. So first thing I want to do, because I have a hard time integrating square root. What we're going to do is we're going to change this to an x to the 1/2 power dx and work on that first. So we're going to go ahead and add 1. Whatever works for you to kind of help you navigate how to add 1 here to a fraction and deal with that. We'll just have a 1/2 plus 2/2. Okay, so our answer here is going to be x to the 2 plus 1 is 3/2, and on the bottom we're going to have our 3/2 plus c. And we're not going to leave a problem like this because nobody wants to look at a fraction over a fraction. We're just going to clean this up a little bit. We're just going to multiply by 1, which is 2/3 over 2/3, to cancel out this bottom fraction. So we can end up with something like 2/3 x to the 3/2, and we have a plus c. So that would be our answer for how to integrate the square root. So every time that you have like a x to the -2, x to the -3/2, x to the -7/5, something like that, change it to a rational exponent so that you go ahead and add that 1 to those problems and not have to worry about, like, well, what happens if I have to integrate something I don't really know how to integrate? We're going to do our best to turn it into a form that you know how to integrate first, and then we'll go ahead from there. Okay, so that's a thing. Okay, let's go ahead and look at a couple of examples here. There is an exception to the power rule. That's what if we wanted to integrate 1/x dx. Okay, just as I said before, we're going to x to the -1 dx. And if we go ahead and follow our rule, we're going to add 1, and on the bottom, we're going to go ahead and 1. So we're going to have, this is x to the 0 divided by 1, 0, and we have a constant. Well, this ain't going to work out so well because division by 0 is undefined. Okay, so we can't really do something divided by 0. That's not going to help. So there's an exception to the power. This is it. So 1/x has its own special rule for integration. So we go ahead and integrate 1/x dx. What we end up with is the natural log of the absolute value of x. Remember that natural logs, you can't take the natural log of a negative number. 1/x is on both sides of the x's, so 1/x looks like this. And we don't know which side of it on, positive side or the negative side. That's why we have the absolute value there. So we end up with stuff over here, negative. We don't want to take that natural log there. So you have to make sure that we're taking natural logs like positive things. Don't let this intimidate you. It's very easy for this natural log. A little intimidating. Look at that. We show you the graph. This is y equals the natural log of the absolute value of x. So try to take a little bit of the sting out of this function by showing us a picture of it. It's not that scary. We just have natural log of absolute value of x. The more you do this, the easier it gets to kind of deal with. There's going to be a lot of times where we can make an argument that this is always going to be positive, so we don't have to worry about the natural log part. So you'll see that in the class as we go forward. But for now, don't forget the natural log, absolute values. Okay, so that is a big exception for the problems here. The other exception is we also have the exponent. Remember that e to the x, what was the derivative of e to the x? That was just e to the x. Okay, and it's going to be plus c because we take this derivative, we go back to dealing with what's going on here. That derivative of constant turns out to be 0. If we want to take the integral of like a kx, which is going to be rather common, and what happens is we get a 1 over this constant, okay, different letter to signify it's a different constant, e to the kx. And again, we have a plus c. Now, if I go ahead and try to take this derivative, if this is my original function, f of x equals 1 over k e to the kx plus c, take our derivative, we get 1 over k times e to the kx. Now remember, there's a chain rule here. So there's going to have a times k at the end of this thing for the chain rule. Again, derivative of this constant is going to be plus. I'll put it in things over here. You don't ever have to write this to show you what happens in the C. So I write this so that you guys can follow along and see exactly what happens. Nobody actually writes this. What's going to happen here is we have a k divided by a k here. So our answer is going to be e to the kx. Okay, and then we have a c for this thing. So when we are integrating e to the kx, the answer is going to be 1 over this k, e to the kx plus c. So that's the other exception to the works for us for those cases. And in elementary calculus, the only rules that you're going to have, the only functions that we deal with, either polynomials, okay, x to some power, x to some value up here. Okay, whether this be a whole number or fraction, whatever, it could be up to square root of 3, doesn't matter. The same rules are going to apply. So if I try to integrate, say, the integral of the square root of 3, this will still work with the power rule because we have a variable raised to some number. Okay, so we're going to end up with x to the square root of 3 plus 1 divided by the square root of 3 plus 1 plus c. And there isn't really a nice way to simplify this. We're just kind of stuck with what that looks like. And I'm sure the square root of 3 plus 1 is a delightful number. We don't really need to know more of the backstory. That you can type this in as a fraction or as a decimal if you want to, but honestly, it's easier to leave it as the square root of 3 plus 1. It's not as pretty to look at, but we're really just dealing with whatever this number is. Okay, so that's what the thing you're going to have to deal with. So polynomials are one thing that we have to deal with. We have 1 over x's, okay, that we have to integrate, which we know is going to be the natural log of x. And now we have e to the kx, which is going to be 1 over k e to the kx plus c. There are some other examples of things that we will have to deal with, but let's worry about these 3 big cases for now. So most of the cases you're going to be dealing with one of these 3 cases. And these are really the only functions that we deal with in this calculus. Okay, so if you're wondering, like, hey, what other special rules do we have to know? A lot of times people will watch YouTube for how to do something, which is great, but they're going to come up with all these trigonometric functions, sine of x, cosine of x, okay, etc. You've never encountered these functions before. They are given to you in Elements of Calculus 1, so we don't worry about taking derivatives here. We certainly don't worry about taking integrals here. Okay, when we take calculus for scientists and engineers, there's a whole mess of other functions that you got to memorize. Okay, but for Elements of Calculus, we have these 3, and that's effectively the 3 that you're going to have to make sure that you know. So those are pretty much the 3 big rules for integration forms. Again, there's some other things that we get to know, but those are the 3 big ones. just like derivatives. Okay, if I wanted to say take an integral x to the 3 plus x to the 5/2, try to take this derivative, take this integral rather, we can separate this out into two different pieces. We can say, okay, this is the integral of x cubed plus the integral, the x in there, integral to the 5/2 dx. We can integrate each one of these things by themselves. So this is going to be x to the 4th, this one is 4. You could either write this as 1 over 4, or you could write this as x to the 4, 4. Both are acceptable, both mean the same thing. And it kind of depends on how much of a hurry you're in, how much this over 4, this 1/4 is going to mess you up. Do the one that causes the least amount of confusion. Plus, and then this x to the 5/2. We are going to have to go ahead and plus this. No rest for the way. So we're going to have trying to integrate x to the 5/2 here. We're going to get x to the 5/2 plus 1. I recommend doing it something like this. And then what are we going to divide by? 5/2 plus 1. And so we'll go ahead and sort this out. So we have 1/4 x to the 4th plus our first constant of integration plus x to the 5 plus 2 is 7/2 divided by 7/2 plus our next constant. So I'll call that C2 for our second integral. So what we're going to have here is 1/4 x to the 4th plus C1 plus, I'm going to go ahead and do the same trick over here too. I'm going to say that's 2/7 divided by 2/7. So that'll cancel out for here. So we'll have plus a 2/7 x to the 7/2 plus C2. Now what happens here is that C1 is a constant, C2 is a constant. If I add a constant to a constant, I will still get a constant. 380 plus 5 would be 8. That's a constant. That'll be okay. So what we're going to do is we combine these c's so that we don't have to track each and every c that we're going on with here. So we have 1 over 4th x to the 4th plus 2/7 x to the 7/2. I'm just going to say plus c, noting that c is equal to c1 plus c2. And you never have to write this for tracking your constants, okay? We just don't do that in calculus. We just track, we say a constant is a constant is a constant. And we just trust that the person who is following our work has had enough calculus that they're okay with C1 plus C2 is equal to C. So that's what we do for that kind of a problem. So that's how we would go ahead and write this down. Go ahead, drop that out of my answer because we wouldn't really include that. Okay, it's just not a thing. So anytime you have an integral of, say, f plus g of x, you can go ahead and say that that's going to be f of x plus the integral of g of x, and handle each one of these things individually. So plus or minus here, plus or minus. Okay, now you might want to say, well, what happens if we have f times g of x? Okay, you cannot do this. Okay, this is a no. Cannot divide these out into the f times g of x is equal to the integral of f of x times the integral g of x. Cannot do this. If you do this, we will both be very unhappy. Okay? You will be more unhappy because you'll lose a lot of points. I will be unhappy because I'm disappointed. But you're not allowed to go ahead and do this. We have a different rule. Again, go back to remembering calculus 1. If we had f times g of x and I wanted to take this derivative, this was equal to the derivative of the first times the second plus the first times the derivative of the second. That's the product rule. We have a very similar rule for integrals that we will eventually learn, but for this review, we're not going to worry about this. You're not going to have any problems, but you're going to have to deal with this. You will have one, but there's a way to deal with it where we actually multiply it out and turn it into an integral that we know how to do rather than trying to mess with this. Okay, so if you're added or subtracted together, you can separate them out. If they're multiplied or divided, we got to do something like the product rule or like the quotient rule in order to get the answer. So you can't just go ahead and do that. So be careful about saying and multiplying together. Every time when I teach this class is very common that students will try to do this and it just doesn't work. Okay, so try to remember that this is a big no-no. Don't write out f times u as the integral of f times integral of g. That's a big mistake. Please don't do that mistake. Okay. So let's go on. See what kind of other examples and other mess we can get into here. Okay, we did some of that. We did some of those. We did some of those. So let's go ahead and take a look at some other examples here. So I got a bunch of examples, and let's say we want to take the integral of 5 over x dx. Now, this is 5 times x to the negative 1 dx. And remember, there's a rule for x to the negative 1. So we have a constant times our value, so we're going to say this is 5 times the integral of x to the negative 1. Okay, just like derivatives, we can slide those constants through if they're multiplied. Same thing goes with the integral, slide those through. So we're going to end up with this equals 5 times the integral of x to the negative 1 is natural log of x, and then we have our c. So that's what this problem, is what this answer will do. We have something like that. Let's go with integral of, say, the natural log of 3 dx. This is another one where in elements of Calc 1, I always get students who have a problem with the constant. Like, what's going on here? Like, technically, you could kind of insert a line of 3 times an x to the 0, and then this would work with our power rule, right? We just add 1 to it. We have a 0 plus 1. 0 plus 1 is fine. That's just 1. So we'd end up with ln of 3 times x to the 1 to the 1. Yeah, you wouldn't have to write this. Plus our c. So our answer here would be x times the natural log of 3 plus c, because the natural log of 3 was a constant. So anytime you have to integrate just the constant with the dx, you just end up with a line. Okay. Y equals mx plus b. I mean, mx would, I showed this to intermediate algebra, they would not be very happy that the slope is the natural log of 3. But being veterans of elements of Calc 1, you can handle this in a slope. So it may not be a pretty slope. We might have to use a calculator to put the answer here, but this would be fine as a slope. That's perfect. And then that's going to be our answer for our natural log of 3. Okay, let's do one that's a little bit harder. Okay, so what if we try this one? I'm going to try the integral of 1 plus x squared over x squared dx. Now, remember I said that you couldn't integrate these guys directly, so you can't just integrate. You can't do this. Like, this would be terribly wrong. Like, you're not allowed to do this at all. Again, both of us would be very, very unhappy if you did this. Okay, this is not the case. What we're going to have to do is we're going to have to just make it like this. We're not going to turn it into integrals. We're going to say this is equal to 1 over x squared plus x squared over x squared, right? If I have two fractions on the bottom, we have common denominators. We could divvy them up like this. That's fine. And then we're just going to have the integral of x to the negative 2. That's what 1 over x squared looks like. Plus, and we have x squared over x squared plus 1. And we have our dx. Now we're okay to integrate this, okay? Because now we turn it into an integral we know how to do. Go ahead and add 1. We have x to the negative over negative plus the integral of 1 is just going to be x. And then technically we would have a c1 and a c2 here, but we're just going to write plus c at the end here. And then we're going to make this pretty, like we know what we're doing. We're going to say this is negative 1 over x, because that's what x to the negative 1 means, plus x plus c. And that's really about how far you would want to take this. And you could take it further, but there isn't really a good reason to want to take this thing further. So that's pretty much how you would want to do something like this. The only thing I might choose is to say this is x minus 1 over x, just so I don't lose this negative sign by having it up front. I hide it somewhere so I don't end up losing it. So that's what she would do with that. Okay, let's read our next one here. Looks like we have the integral of, and I got an x plus 1 times, and we have our x minus 5 here. Again, we can't divide this out and take the integral. I wish we could. We cannot do this. We can't say this is the integral of x plus 1 times the integral of x minus 5. Don't do this. This is terrible. Okay. Well, how do we integrate this? Well, we have to do it the hard way. We have to multiply this stuff out first before we can integrate. So we're going to say this is the integral of x times x is going to be x squared. We're going to have positive x minus 5x's minus 5. All of this has a dx attached to it. So we're going to go ahead and say this is the integral of x squared. 1x minus 5x, we're going to have a minus 4x's minus 5. And we're going to go ahead and do our dx that way. Okay, so let's go ahead and integrate. Now, see, now we have an integral that we are used to integrate. Functions that we are used to integrate. That's pretty much the whole thing for this first section. We're going to turn anything that looks unfamiliar into something that looks familiar. So we're just going to say this is x cubed over 3 minus, rather, minus 4x squared over 2 minus 5x plus c. Even though I have a c1 plus c2 plus c3, just going to make it a c. And then we're going to make this a little bit prettier. You could leave it x cubed over 3. That's perfectly fine. If you want to turn it into something like this, that's perfectly fine too. The only reason I do that is 4 over 2 is 2. Okay, minus 5x plus c. We have it in 3, 2, 1 descending area, descending form rather. So that would be our answer for something like this. How does that feel? So let's see, do we want to do one more that's on the harder side? Let's do one more that's on the harder side. Let's do the integral of x to the 1/3. So I told you it was going to be a harder one. Plus 5x to the 1/4. We're going to divide this by the square root of x. So what we're going to have to do is, again, we have pluses on the top and one thing on the bottom. So we can go ahead and divide each term. We could say this is going to be integral of x to the 1/3 divided by x to the half, that's what the square root means, plus 5x to the 1/3, 1/4 rather, divided by x to the 1/2. Again, these are both dx's. So way back in algebra, you had rows of exponents where you subtracted these guys. So we're just going to come over to the side here and say, okay, what's 1/3 minus 1/2? I think that was negative 1/6. And then we have 1/4 minus 1/2. So a quarter minus 50 cents. We end up. Okay, so we'll go ahead and integrate this. We're going to have the integral of x to the negative 1/6, it's 1/3 minus 1/2, top minus bottom, plus 5, we pull that off to the side, integral x to the negative 1/4. There's constants like this will float through the integral sign. Then we have to go ahead and integrate this. This one's a little bit trickier, so again, we're going to add 1. 6 over 6 looks like 1. And then we'll divide by negative 1/6 plus 6/6. Here, we're going to say plus 1. We have negative 1/4 plus 1. That's what we're dividing by. So let's go ahead and clean this up. So we have x to the negative 1/5 plus 6/6. That's 5 over 6 divided by 5 over 6. Okay, plus 5 times we have x to the Negative 1 plus 4 is going to be 3/4 divided by 3/4. Now I've integrated, we have our plus c, right? So we'll go ahead and clean this up by multiplying top and bottom by 6/5, 6/5. Okay, again, you probably wouldn't write this step doing this so you can see it's coming from and know what you're doing this problem yourself. Okay, you would probably just flip this thing, go ahead and deal with this. So we'd have a 6/5 to a 5/6 plus, and then we have 5 times 4/3, right? This is going to cancel out. So we're going to have 20/3 x to the 3/4 plus c. That's what we're going to end up with, okay? So again, we did not integrate top and bottom. We divided these things first before we went through the difference. Now, just remember, if you have something like an x squared over 1 plus x squared, we can't take this and divide this out. Okay, we're kind of stuck with what's going on here. So this is not an integral that we will have to do for actually ever, because our class does not work with this integral. But you can't go ahead and undo the division this way. If it was flipped, then we could do that. But you can't flip inside of it, and you don't want to do that. You don't want to take reciprocal for anything. There's no equals to. Okay, we're not allowed to change how much is going on. So this one, for our purposes, right now, we actually can't do this problem. Okay, so you're kind of stuck with, no, sure that looks very pretty, but I can't do it. So again, going back to, we only have polynomials or things that can be turned into polynomials. We have 1 over x's or things that can be turned into like a 1 over x. And then we have e to some function, some constant, like e to the 3x. If I want to integrate e to the 3x dx, it will just be 1/3 e to the 3x plus c. If I took this derivative, we would get back to e to the 3x. So those are the only 3 that we have to work with. If they throw you something where it's like, looks like I have to do f times g, like back up to here, you have to multiply them out. You will learn other methods, and you don't have to do this all the time eventually. But even with other methods, one is pretty straightforward just to multiply out. It's still just multiply. Okay? So hopefully that rattles the cobwebs off of what you remember from elements of Calc 1. This. If this felt really new and really awful to you, start practicing some of these early ones, because the more practice you get, the better off you're going to be. Okay, so I'm going to go ahead and leave you with that for the lecture. And welcome to Elements of Calc 2. I promise it will get harder if this was not hard enough, but that's, I think, for a first lecture, that's great. I will see you in the next video. Thank you.